Okay, so let's start with an example problem. We're going to go a bit past what it technically asks for. So we've got two cables here tied together at C that are supporting this load. I want to draw the free body diagram needed to determine the tension in that particular, in those cables. So first off, simple enough with FBD. So we are going to start here. Let's use this real estate over on the right here. So we're going to be essentially, in order to figure this out, we need to take the free body diagram of C. So I'm going to draw a nice little dot there for C. Label it C. And we'll just apply the forces that we know are acting upon it. So, first off, we've got the load. Let's call the load P. We can figure out what the magnitude of that load is. So we know that it is supporting a load that is 1,600 kilograms. And we can assume, it's not necessarily stated, but we can assume that it's acting in Earth's gravity. So multiply that by G, 9.81 meters per second squared, times kilograms, gives us our force in newtons. That's the gravitational weight of that object. 15.7 kilonewtons is basically the tension in this tiny little this segment here. So the other parts of the free body diagram that we're going to need. We're going to need this force here. Let's call that CB, since it's the tension acting in the CB along that cable section at CB. And then we're also going to have AC. Now, one thing I would like to point out here is that when I drew these, I drew the angles correctly. But I would like to point out we don't necessarily know the magnitudes of these yet. They're not going to be the same. They would be the same if for example, this thing was passing through what we call a frictionless ring. Then essentially this would be one cable that had a uniform tension throughout it. But we know that the magnitudes of those aren't the same, because if the magnitudes of those two things were the same, then essentially we wouldn't be in equilibrium here, because this section AC here is at a, it goes off further in the horizontal than CB does. So as a result, CB and CA, if they had the same magnitude, would have different different horizontal components of the resultant force. So anyways, one next thing we're going to do here is to figure out what our angles here are. We're going to need that to do our free body diagram too. So I've gone ahead and labeled the dimensions here. And essentially, when we want to find out what these angles are, we just take the inverse tan. So theta b, that's going to be the inverse tan of 400 over 960 millimeters. So 400 over 960 is 0.41666666. Inverse tan of that, 22.6 degrees. 22.6 degrees. And likewise, inverse tan of 1100 divided by 960 for our theta, for our angle A there. That's going to be 48.9 degrees. So we got those numbers there. We've got our free body diagram there. That's essentially all the question asks for. So I'm going to keep going, and I'm going to actually determine what the tension in those bodies are. So essentially, what we can do is we can find our equilibrium equations. So we are working with the points. So the first and kind of the first step that we should probably be doing here, we know that the horizontal component of this section AC, of the tension from AC here, needs to equal the horizontal component of the tension from CB. That's essentially just us saying that the sum of the forces, let's see, oh, I did forget to define our axes. So let's go ahead and do that. So assuming that the x-axis is pointed off to the right here, the y-axis is pointed off to the pointed upwards. So with our axes defined, taking the sum of the forces in the x direction, that's all equal to 0. We know this because we're doing an equilibrium question. So therefore 0 is equal to, we know that the horizontal component of P is 0 because it's that, that's gravity. It doesn't act horizontally. So we've got just the horizontal component of this force CB here, which is going to be the CB times the sine of this angle. So CB times the sine 22.6 degrees. And then that minus, because it's acting in a different direction, minus AC times the sine of 49.8 degrees. So we can rearrange that and essentially solve for CB and AC in terms of one another. So the simplest way to do that, let's just go add AC to the other side here, and then divide by that sign there. CB times sine 22.6 divided by sine 48.9. So that works out to AC being just about half, just over half of CB. AC is equal to 0.509 0.99, so let's make that 0.501. Sorry, 0.51 CB. And again, we did expect AC to be smaller, just because otherwise just because it needs to be smaller because the horizontal component would otherwise overpower CB there. So we've got those two in terms of one another. The next thing we can do is take the sum, is a terrible sigma, take the sum of the forces in the y-axis and have those equal to 0. So based upon that, we know that 0 is going to be equal to, again, we're both working with portions of AC and CB here, except this time instead of taking the sine of these angles, we're taking the cosine of those angles. We want this portion here, not that portion there. So we're working with AC times cos of 48.9 plus, and again I'm adding plus because both of these are acting in the positive direction. They're both indicated as being in the positive direction, and they both actually are going to be in the positive direction. So plus CB, no, not CO, CB times cosine of 22.6 degrees minus, again because this P here is acting in the negative direction, minus 15.7 kilonewtons. Alright, so we've got that. That doesn't let us solve for this immediately, but we do have this relationship right here. So we can take that and basically plug that into here. We'll also move the 15.7 over to the other side of the equation. So 15.7 kilonewtons is going to be equal to 0.51 CB times cos 48.9 degrees plus CB times cos 22.6. And basically we can factor out our CB's there. CB times 0.51 times cos 48.9 plus cos 22.6 degrees. And then we can just go ahead and figure out what that value there is. So 0.51 cos 48.9 plus cos 22.6. So that gives us 1.259 CB is equal to 15.7 kilonewtons. So 15.7 divided by that. So CB we get solved for 12.5 kilonewtons. Here, actually, let's go to 4 significant digits, 4 digits for that. .48 kilonewtons. And then AC, we can again solve for that by multiplying that by 0.51. .36 kilonewtons. And again, I'm going to the same significant digits as we kind of talked about earlier, where if it starts with a 1, going to 4 significant digits isn't terrible. If it starts with anything else, going to 3 is reasonable, because the general accuracy you can usually expect to get is about 0.2%. Anything more than that, you're really stretching it. So those are the values that basically would allow us to have that weight suspended by ropes in that configuration.